In this lecture, we will learn the applications and properties of Jacobians. The first property of Jacobians is property 1. Let u is function of x and y, v is function of x and y, then Jacobian of uv with respect to xy into Jacobian of xy with respect to uv is equal to 1. It means Jacobian of uv with respect to xy is inverse of the Jacobian of xy with respect to uv. So this is very useful property, and I am not going to prove this property in this lecture. If you want a proof, I will make a separate lecture for to prove all the properties I will discuss here. So here I will use the property to solve the questions. So let us take a question. Problem. Let u is equal to x, y, z, v is equal to x square plus y square plus z square, and w is equal to x plus y plus z. Here one thing that I should recite is that I have discussed this property in only two variables, but the same thing holds for any number of variables. If there are three variables, the property hold. If there are four variables, the property hold as well. So for an example, if you have three variables, then Jacobian of u, v, w with respect to x, y, z into Jacobian of x, y, z with respect to u, v, w. This is 1. And if there are more variables, 4, 5, 6 or n number of variables, the property will hold as well. So here this u, v and w are given as a function of x, y and z, and find Jacobian of x, y, z with respect to u, v and w. So you can see that because u, v and w are functions of x, y and z, so we cannot directly find the Jacobian of x, y, z with respect to u, v, but we can find Jacobian of u, v, w with respect to x, y and z. So as a thumb rule, we will remember that Jacobian that we can find is Jacobian of functions with respect to the variables. This is a thumb rule to remember. So functions are u, v and w. So we will find Jacobian of functions with respect to variables. Variables are x, y and z. So let us calculate it. Solution. Jacobian of u, v and w with respect to x, y and z. This is equal to del u by del x, del u by del y, del u by del z, del v by del x, del v by del y, del v by del z, and del w by del x, del w by del y, del w by del z. So this is Jacobian that we are going to compute. So what will it yield? So del u by del x is yz, yz, del u by del y is xz, and del u by del z is xy. This is one row. And what about the next row? Del v by del x. Del v by del x is 2x. Del v by del y is 2y. And del v by del z is 2z. And what about the final row? So del v by del w by del x is 1. Del w by del y is 1, and del w by del z is again 1. So this is the determinant, and you can simply open the determinant to find the answer of Jacobian of del vw with respect to xyz. So just I am leaving the simplification for you as a homework, because you already have the knowledge of simplifying determinants. This property is sometimes also referred to as j dash is equal to 1. What is j and what is j dash? So if you term j as u v w with respect to x y z, then j dash is directly its inverse, means x Jacobian of x y z with respect to u v w. So we will take a question to verify that jj dash is equal to 1. Example, let x is equal to uv and y is equal to uyv. So verify that jj dash is equal to 1. So so first we define j. J means Jacobian of xy with respect to uv. So we should find it. So what is this? Xu means del x by del u, and xv del x by del v, yu yv. These are the partial derivatives. So del x by del u means v, del x by del v means u, and then del y by del u means 1 by v, and finally del y by del v is minus u by v square. So once you open this minus u v by v square minus u by v, this into this. So you can see that 1v is getting cancelled here, so this will become minus u by v minus u by v, means you will get minus 2u by v. So this is our j is equal to, we have calculated, j is equal to minus 2u by v. This is our j. Now by the theorem jj dash is equal to 1, but we have to verify it. So how should we verify it? So for this we need to write u and v as a function of x and y. So let us do this. Consider x into y. So what is this? This is uv into uyv, means u square, and this gives u is equal to square root of xy. I am dropping the plus minus sign. You can consider minus also. So number 2, x, consider x by y. So this is uv by u into v. So this is v square. So this implies v is equal to square root of x by y. So now we should compute. So Jacobian of uv with respect to x by y. So u is equal to square root of xy, and v is equal to square root of x by y. So now compute Jacobian of u v with respect to xy. So this is ux, uy, vx, vy. What is this? Ux is equal to y by 2 root x, square root of y by 2 root x. And what is uy? This is square root of xy 2 root y. What is v by x? What is vx? Vx is 1 by 2 square root of xy. And finally, what is vy? This is y square root of xy to y root y. So just calculate it. What does it yield? So you can see that you can multiply this minus this. So root y will get cancelled. Root x get cancelled. So I am writing everything. Root y by 2 root x into minus root xy 2y root y and minus this root x by 2 root y into 1 by 2 root x root y. So here this root x will cancel in numerator and denominator, and root y will cancel in numerator and denominator. So what you get is minus 1 by 4 y, and minus in the next term root x is again cancelled out, and root y is y. So this minus 1 by 4 y. So finally we get minus 1 by 2y. And because you know that what is y, so y I am writing here separately. Y was given as u by v. Y was given as u by v. So what is this? This is minus 1 by 2 v by u. So remember that we obtained Jacobian of xy with respect to Jacobian of uv as minus 2u by v. So if we take this product, so we have already assigned the name j to this. So this is j dash. So now j into j dash is equal to minus 2u by v into minus 1 by 2 v by u. So each v cancels v, u cancels u, and this is finally 1. So what we did, we have proved that jj is equal to 1. Now we take the next example. R is equal to e to the power x sec y, and s is equal to e to the power x tan y. We have to find out Jacobian of xy with respect to r and s. So we will first find out Jacobian of rs with respect to xy, then invert it as our property tells. So Jacobian of r and s with respect to xy, this is what? Del r by del x. So this is e to the power x sec y, then del r by del y. So this is e to the power x sec y tan y, then del s by del x, this is e to the power x tan y, and del s by del y, this is e to the power x sec square y. So you can open the determinant, it will become e to the power 2x sec y sec square y minus tan square y. So the bracket sec square y minus tan square y is 1. So we obtain e to the power 2x sec y. So this is Jacobian of rs with respect to xy. But we need Jacobian of xy with respect to rs. So by our property, Jacobian of xy with respect to rs is inverse of Jacobian of rs with respect to xy. So this is what? E to the power minus 2x cos y. Now we will take one more example. So let us find the Jacobian of if u is equal to xy and v is equal to x plus y by x minus y. Then find the Jacobian of xy with respect to uv. So watch, mark that u and v are functions of x and y. So we can first find the Jacobian of uv with respect to x and y. So Jacobian of, so you can also see that u is easy to differentiate, but v is not so easy. So first find all the partial derivative. This is better to find partial derivative first. Each function is complicated. So first we will find partial derivative. So ux is equal to y, uy is equal to x, and vx is equal to, apply the quotient rule of differentiation, x minus y into 1 minus x plus y into 1 divided by x minus y whole square. So this is equal to minus 2y divided by x minus y whole square. Similarly, vy will be x minus y into 1 minus x plus y into minus 1 divided by x minus y whole square. So this will become 2x by x minus y whole square. Now write the Jacobian of uv with respect to x and y. So this will become Jacobian of uv with respect to x and y and x minus 2y by x minus y whole square and 2x by x minus y whole square. So open the determinant, you will get 2xy by x minus y whole square plus 2xy by x minus y whole square. So this will be 4xy divided by x minus y whole square. So this is the Jacobian of uv with respect to xy. But question demands the Jacobian of xy with respect to uv. So as our property, we will get this is equal to x minus y whole square divided by 4xy. Now we'll take a final example. So example, last example, this is if x is equal to r sine theta cos phi, y is equal to r sine theta sine phi, and z is equal to r cos theta, then find the Jacobian of r theta phi with respect to x, y, z. So initially we will find Jacobian of x, y, z with respect to r theta, and then with the property we will invert to find the result. So first you can write all the partial derivatives. Partial derivative, when you differentiate x with respect to r, this is sine theta cos phi. When you differentiate x with respect to theta, this is r cos theta cos phi, and the derivative of s with respect to phi is minus r sine theta sine phi. Similarly, yr is equal to sine theta sine phi, y theta is equal to r cos theta sin phi, and y phi is equal to r sin theta cos phi, and finally zr is equal to cos theta, and z theta is equal to minus r sin theta, and z phi is equal to 0 because z has no component of phi. So now we will put these partial derivative to find our Jacobian of xyz with respect to r, theta and phi. So let us try to find. So now Jacobian of x, y and z with respect to r, theta and phi is, this is sin theta cos phi, then r cos theta cos phi, and then minus r sin theta sin phi, then sin theta sin phi, and r cos theta sin phi, and r sin theta cos phi, and in the final third row cos theta minus r sin theta and 0. So open the Jacobians. Before opening, you can take r common from the second column and third column. So once you take r common, it will, and then open along the third column because one element is 0, so you need to open with the rest of the two elements only. So this will become 1 r square common from second row, 1 r square common from, and sin theta is also common from the third column. So r common from two columns, so it will become r square, sin theta common from third column only, so r square sin theta, and the rest of the things I am going to open. So this will become only sin phi will be here, so minus sin phi, so you will get minus sin phi, and open rest of the elements. So this sin theta square sin phi, this I am indicating you, though you need, you already know how to open. So once we open with this sin phi, this is sin square theta minus sin square theta sin phi, and then cos square theta sin phi. So you will get, I am writing in red color, minus sin square theta sin phi minus cos square theta cos phi. So this is what you got with the first element in the third column, and with the second element in the same column we will get minus cos phi, and open this also. So I am deleting this markup, so open with the cos phi. So with cos phi you will get this sin square theta cos phi, and this cos square theta cos phi again. So this, so this will become minus sin square theta cos phi minus cos square theta cos phi minus cos square theta cos phi, this. So you can take sin phi, sorry, this was sin phi, this sin phi sin. So you can take sin phi common in this row. You can take this sin phi and sin phi common. So minus sin phi taken common, sin square theta plus cos square theta will become 1. So you will get r square sine theta, and then this minus minus is plus, so sine square phi, because you took one sine phi common. And in the same way here you can take this cos phi and cos phi common with minus, so minus minus will become plus, and sine square theta plus cos square theta will become 1. So you will get cos square phi, so this is again 1. So what is the final result? R square sine theta. So this is what we obtained, Jacobian of xyz with respect to r theta phi. And finally Jacobian of r theta phi, because our question demands us to find this Jacobian of r theta phi with respect to xyz. So using our property, this will become 1 by r square sine theta. So this is very interesting Jacobian, very interesting. When you will evaluate triple integrals of this form, this f x y z dx dy dz, and you take the transformation as taken in this question, x is equal to r sin theta cos phi, y is equal to r sin theta sin phi, and z is equal to r cos theta, then this dx dy dz will be replaced by r square sin theta, r square sin theta dr d theta d phi. So this is why this Jacobian is important to us. This is not the part of this question. I just indicated that during the triple integration you will need this. So in this lecture we have attempted a lot of questions and tried to understand the property first of Jacobians, and in next lecture we will try to understand and try to solve the questions with the property 2 of the Jacobians. So it is recommended to watch the next part. Thank you.